All right. So I guess now our audience is arriving.
Are they in yet?
No attendees. Oh, yeah. No. Yeah. Maybe you can all say hello in the chat if you see the chat so we know that you're actually in. Oh, yeah.
Yeah, that's good.
Here we go. Nice to see you, Jack. All right. So we have 34 and counting. Brilliant. Yeah. So not going to start right now. We're going to wait for another 2-3 minutes, but it's going to be pretty much me for 2 minutes, and then we are going to have Max showing us for 45 minutes what PDF can do for catalyst development. Huang is with us up here. She's our founders associate and will help us with admin and seeing all the questions that you have. If you have questions, please put them in the chat. We will get to them in the Q&A, or you can ask them in the Q&A if you want to save them for later. So I think we started maybe one past, so everybody has a chance to get into, and we're at 36 already. Really nice seeing everybody, seeing a couple of familiar names. Really nice. All right. So, welcome to our first webinar of 2026, Total Scattering and Pair Distribution Function Analysis, Applications for Catalyst Development with Maxwell and myself, Sebastian. Who doesn't know, I'm the CEO of Momentum Transfer, and Max is our COO, and I will introduce him later. Again, I will go real quick because Max has so much to cover through our agenda. So we will cover powder diffraction and total scattering, what is pair distribution function, and then have a bunch of applications. You will see how to start with PDF right away using momentum transfer, and then we get into Q&A. So why do we have this session? Because Catalyst R&D is demanding and is getting more demanding all the time by increasingly demanding processes. Of course, we have sustainability KPIs, and we have competitive pressures on suppliers and customers. And what we want to show you today is that PDF is a tool that can actually help you to design better catalysts faster by improved detection limits, by having more information over wider parameter space, and detailed insights into the nanostructure and microstructural properties. So Maxwell is going to talk about this, and he is, besides of our COO and co-founder, he got his PhD from Columbia University from Professor Simon Billinge, and did his postdoc at the Max Planck Institute in Stuttgart for solid state research with Professor Dennebier. So without any further ado, what can X-ray scattering and PDF do for us all? Max.
Awesome. Thanks, Sebastian. And yeah, I will try to answer that for you. So, I mean, just to get right into it, I will start with a short background on powder diffraction and total scattering, although I'm not really going to get too deep into like the theory or the how-to in those respects, but just to give you guys a little bit of context of method fundamentals. But also just to contextualize what we're doing here. I mean, I want to just sort of overview like what are the high-level goals of these structural characterizations and how we drive materials development. And there's a few things that I think about, which is identifying what phases are present in our materials and how much is in there. And that's like sounds like a trivial thing, but it's a really important thing because there's no such thing as a pure material. There's only purity down to whatever you specify is the limit of what you care about. And in many, many cases, very dilute impurities or side phases or other, surface structures can be very important to the functionality of materials. And if you don't know what's in there, it's hard to understand all aspects and angles of why your materials behave the way they do and which aspects you should focus on in your development. Of course, there's determining actually what the materials are in the sense of, is it something that we know that you have available in databases, or are you making brand new materials? And if making new materials, how to figure out exactly what they are. And finally, correlating all of this structural information with actually what you're doing in the synthesis and processing steps, and which properties are being determined by which aspects of the structure. So X-ray powder diffraction is a great tool to study this because it gives you a whole wealth of structural information, microstructural information about your materials that you can use to contextualize the relationship between synthesis and properties and what decisions to make. So you can get information about the expansion and contraction, the density of the material, the crystal symmetries which govern certain properties, the atomic structure, conformations in molecular materials, all the way to binding interactions, microstructure, strain, and things like that. There are lots of other properties where these things don't come out so clearly in these typical sharp diffraction peaks that you have from X-ray diffraction. And this shows up as diffuse scattering in our signals. And these are properties like defects, like distortions, nanostructure, and amorphous phases. And with standard analysis, that being typically Rietveld refinement, these things are difficult to access, and we're typically throwing out some of the information that contains those details. And so we want to explore that. Why do we want to explore that? Because for nanocatalyst development, we run into exactly those problems. Okay, we have important components that are either amorphous in some sense, or rather ultra small nanoparticles or domains. We have significant amounts of surface structures that are very important to functional interactions in heterogeneous catalysts. We have impurities that are present that may be advantageous in some cases or actually deleterious to the performance in others. And we have wide distributions of particle sizes and morphologies, and those can also play an important role in surface structures. Okay, so we need to be able to parse this information from our measurements. And how does this manifest? Well, you can think about kind of this space of how well your samples diffract and how representative your samples are of actually the bulk materials that you're interested in understanding. So in some sense, we often think of the gold standard being single crystal diffraction because you get the best separation of all of the three-dimensional structural information. But you do single crystal typically on a single crystal. And how representative that is of your kind of bulk material that you're using is not always so clear. And so as we move to looking at distributions of our sample, we have higher statistics on different crystallites and different domains, and you get a better representation of the bulk average of the material that you're making. But the side, kind of disadvantage of that is now my domains are getting smaller when I go to microcrystals or nanocrystals, and my diffraction signal is getting broader and broader, and thereby, again, more difficult to parse out all of this structural information. There's other things to consider for catalysis, which is often that we're suspending particles on supports, and there you again are still in the space of having a representative sample, but now you have much less of the material in your scattering volume is actually the target of what you're trying to understand. And so now you have a big percentage of your information is not actually the part that you care about. So you have to actually be able to extract that out as well. Okay. And then we run into this problem as our domain sizes get smaller and smaller and less well structured, and we have larger contributions from supports. We have very diffuse signals, and it's difficult already to separate out what part of that is actually the part that I care about. So I have to do this separation, and then I also have to figure out how to extract this information about the identity of my materials, about coordination environments, local structure, phase structure, etc. Okay, and that's what I want to try to show you how to do with total scattering. Okay, so now I'm just going to do a brief theory just to kind of show how we're getting that. And then we go back to sort of the fundamental equations of the scattering, and starting with the amplitudes. This is just a Fourier transformation of the atomic density or the electron density distribution for X-rays in my material, okay? But when we do X-ray diffraction and scattering measurements, obviously we're not collecting the amplitudes, we're collecting intensities. And so we have to take the square modulus of this. And the only thing that I really want you to take away from this is in kind of multiplying this by itself, we actually end up taking, do I have a laser pointer in here, by the way? Not sure. But anyways, you can see in the highlight part in red here that we're taking the difference in the positions. So this vector between different atoms, and we're getting information about the relative distances between atoms or scattering centers in our material, okay? And of course, we can replace the electron density distribution in the case of X-rays with our form factors, or if we were to work with neutrons with the scattering lengths. But the important distinction is we're getting information about the relative positions, not absolute positions. And going back to this idea of single crystal scattering, okay, that's great when we get sort of, within our assumption, infinite periodic systems, then we can define everything by a unit cell, and we can condense the scattering information down to the atomic positions in our unit cell. Okay, and that's great. That's a really convenient sort of emergent behavior of these systems that allows us to make the calculations tractable and simplify fitting models. But there's not really a lattice there. This is just a mathematical concept that emerges from the behavior of the atoms. And so when we deviate from these assumptions being, suitably correct, when we go to these nano systems, we don't really have such a good matchup between this assumption of infinite periodicity anymore. And so defining the system in that way becomes to the point of being incorrect, that it makes it very difficult for us to be quantitative about what we're doing or to extract the information that we're looking for. So we need to go back to thinking about atoms and not necessarily mathematical lattices. Okay, and so when we take single crystal diffraction and we go to a population of crystallites and start doing an orientational average, now we're overlapping all of our diffraction patterns in all directions and diffuse scattering when we're not satisfying the Bragg conditions, and collecting all of this information into one overlapping pattern. So we can do a spherical average on this this exponential term, and we get basically the Debye equation. So this has this sinc term, and now we're looking at the magnitude of these values and not the vectors anymore. Okay, and the point here again is that we can separate out the information that comes from the structure, which is our distinct scattering, and the self-scattering, and now we have a function that is not assuming anything about the periodicity of the system. It's just allowing us to predict what the scattering should look like for a collection of atoms, irrespective of the extent of the matter or the coherence of the structuring. Okay, and so we want to do these measurements. Typically, we're working at the synchrotron, and we want to collect really, really high statistics information, and we want to collect scattering patterns over a very wide angular, or rather Q range, so that we have a high resolution to the real structure of the material. So we use monochromatic beams. We typically use very high energy. We're working actually at 75 keV, but that allows you to collect to a very high resolution with a large area detector. and also minimizes absorption. So we're oftentimes dealing with quite heavy atoms with catalysts. And yeah, we want to have really high flux beams to get good signal to noise in those high Q regions where our statistics on the actual coherent scattering component become very low because your Compton scattering starts to dominate and your X-ray atomic form factors are significantly diminished in these higher Q range. Okay. And then there's a lot of other considerations that have to be made to get rid of all of the additional systematic effects from the measurement geometry and parasitic scattering contributions that don't contain any of the coherent scattering information that we're interested in. So this is everything from proper correction of the detector geometry, of absorption, polarization, all the way to getting rid of background scattering and removing Compton scattering, fluorescence, multiple scattering, and these kind of things that are inherent in the scattering process itself. Okay, and so we're still collecting X-ray powder diffraction pattern. We don't necessarily care as much about the reciprocal space resolution in this case. So you can see the patterns may be a little bit broader in some cases. But the important point is that we're collecting over a wide range of Q. And this is interesting when you look at it, because oftentimes you see patterns like this and it looks like there's no structural information in these high Q ranges. So from roughly 7.5 inverse angstroms on, it looks like a flat line. And again, this is because the structural information in that range is a very small percentage, typically, of the total signal that you're scattering onto the detector. So we have to correct the data to extract out and amplify the coherent information that we're looking for. And so how we do that is, well, basically we try to remove to the extent possible the Q dependence of these form factors, and also getting rid of some other diffuse components that don't contain structural information, like this second term in the reduced structure function here, which is the Laue monotonic diffuse scattering. And then we amplify by Q, which is also amplifying the magnitude of the signal at higher Q values. And once we do this successfully, then we Fourier transform that information to get the pair distribution function. Okay, so what is the pair distribution function? Again, there's a lot more that goes into sort of deriving everything between these, and actually we'll do another discussion on sort of how to PDF in 2 weeks. So I will get a little bit more into that in that session. But here I just want to give you a brief primer sort of on how to read the PDF, so that when we get into the applications later, you kind of know what you're looking at. Okay, so essentially the PDF is a scaled, sort of modified histogram of atomic pair distances in your material. Okay, so if I sit on any given atom and then look out into my local environment and travel in a sort of spherical shell, as soon as I hit the next atom, then I register a unit of intensity at the distance between myself and that neighboring atom. And then the number of units will combine to give me the intensity in my peak. So the intensity of that peak is related to the number of neighbors, and the position of the peak is related to the distance between the two atoms. Okay, and I can keep traveling out in further distances and get a peak every time I hit a new coordination shell. Okay. The baseline that these peaks sit on in this form of this histogram has to do with the overall atomic density of my material. So this is minus 4 pi r rho naught being the atomic density. The width of the peak has to do with both static and thermal displacements. So it's telling me the distribution of distances between a certain pair type, okay? Because we have 0-point motion. We have also static displacements based on, if I'm in proximity of vacancies or surfaces, I might have a slightly different equilibrium distance. And then, of course, we also have phonons in the material, thermal vibrations that are activated at higher temperatures, and that's also increasing the width as well. Okay, and so if I look at nearest neighbors and I move an atom, then my neighboring atom will tend to move with me, and this is called correlated motion. So this actually leads to a sharpening of the distribution. And you can imagine if I move anti-correlated, then this would result in a broadening of the distribution. Okay. As I said before, the integral of that peak is related to the coordination number. And then if we look at sort of the longer range properties of the signal, if I look at the damping profile of those peaks, this has to do with the size of my coherent domains, because as I approach either the surface of a particle or a grain boundary, or for instance, I just have enough sort of defects built up in the material, I will reach a point where I can no longer predict where the distance of the next atom pair will be. Or if I hit a surface in a nanoparticle, there just is no further atom. And so there's no contribution of intensity in those ranges. So this decreases the peak intensities as I go to higher distances. And the shape of that damping profile has to do with the shape of the particle. Okay. And then also there's a modification of the baseline that comes here. Again, I'll probably talk more about this in a couple of weeks, but this actually has to do with the forward scattering from the particle, actually the small angle scattering, and the removal of this contribution modifies this baseline. And finally, the distance at where I have no peaks is essentially the average domain size. I also just kind of provide to you guys a review paper that we wrote quite a few years ago, but this is a really, I think, a good introduction to the kind of fundamental theory, the math of how to derive all this stuff, and then lots and lots of applications for information that you can get from pair distribution function analysis. So now I'll kind of switch gears and get into a bit of the applications. And the first one that I'll start with is, again, going back to this idea of detecting and quantifying what phases are present, and specifically in nanoparticle catalysts, because I think that's where the advantages of including PDF in your analysis really start to become much more apparent. And so, you know, the thing that I've been doing some work on with various collaborators is this idea of moving away from pure noble metal catalysts to more earth abundant systems, because we just need cheaper alternatives and things that are more ecologically friendly. And so there's a lot of work going on in developing 3D transition metal based catalyst systems, either explicitly or at least to reduce the amount of noble metals needed in the catalyst. And so there's a big push going on trying to develop catalysts with manganese, iron, cobalt, nickel, copper, for instance, and then also often these other components that I have in the dash lines here, so titanium, vanadium, chromium, zirconium, niobium, as separate systems or often as doping atoms, and all towards getting a lower cost of production, better sustainability and availability. Also because you have lots of different chemistry that you can do here, so you have more capability to tune things like morphology, particle size distributions, surface states, and really have more flexibility in what you can do with designing specific reactivity profiles. And also there's some interest in certain cases with lower toxicity, and that has more to do with the regulation of noble metal molecular complexes, so for more like photocatalyst applications. But that's also something that is interesting. And so again, we go back to, okay, I have distributions of small nanoparticles, and I want to extract out all of this structural information so I know what I'm actually making. But when we look at how the diffraction patterns develop as a function of domain size, I start to see that going from microcrystals to nanocrystals to clusters significantly degrades the width and the quality, the statistics of my peaks. So the intensities go down by potentially orders of magnitude, and the ability to decouple these peak contributions to actually resolve the positions and relative intensities becomes relatively much more difficult. So how do we manage this? right? So I'll show you exactly how we can do that with PDF, and starting with this example. So these are some really fantastic collaborators that I've worked with from Wits universities, as Victor and Dean, and they've been developing these mono, bi, and even trimetallic transition metal composites, particularly for hydrogen evolution, oxygen evolution reactions. And actually what we started with in trying to do kind of more extensive structural investigation was these nickel oxide, cobalt oxide systems, and they're depositing these metal and metal oxide nanoparticles onto hollow carbon sphere supports to keep them from reaggregating. And they actually get some really quite interesting performance. So for instance, they get quite good performance with particularly hydrogen evolution reactions. But yeah, the goal is to understand why, so that they can continue to develop these. And we see quite complex phase behavior. So it's very interesting, I think. So this is what the diffraction pattern looks like. And I should say, you don't want to do PDF analysis completely independent from your kind of standard diffraction analysis, because that is always the good starting point to understand your system up to the point that you can with standard techniques, so that you really know what else you should be looking for in the PDF. And so we try to do kind of standard search match phase detection with patterns like this. And it's not great because the peaks are really broad, but since the structures for these materials are relatively simple, that makes it a little bit easier in this case. So we can go in and ID our peaks, and we find sodium chloride type nickel oxide. And you can see in the PDF that we can confirm that identifies the majority of the peaks present in the signal. We can find a few other things here. So we can see there's two small little peaks at lower angles. And it turns out that that's actually metallic nickel. And this is a little bit harder to see by default in the PDF if you didn't know anything else. But actually you can see that there's a tiny little peak around 2.5 angstroms. And that's actually the nickel-nickel pair distance, okay? And so with that, we kind of have like a full description of our patterns, and we don't see any major discrepancies left over. So we're pretty happy with that. And so we can do that for the nickel oxide and the nickel cobalt oxide systems and check what are the results we're getting. And we actually see a really good consistency in the quantification. So around 96, 97% of nickel oxide, a few percent of nickel, and we also get a good match in the domain size estimates for the particles. And you can see actually is quite a significant fraction of very small particles in the 1 to 5 nanometer range. Okay. Now I jump to the cobalt oxide system, when this is where it gets a bit more complicated. On the one hand, you already see in the diffraction pattern, there's a sort of much more complex phase distribution. So again, we go through the same process. So we find Bortsite type cobalt oxide. Again, look at the PDF, and it looks quite good. We find sphalerite type. Okay, that also looks pretty good. And actually, it already becomes much more difficult to find here because I only have maybe 2 to 4 peaks that I can really reliably find. But helped with some pre-knowledge of the system, then we again find this sodium chloride type cubic cobalt oxide. And now I sort of look like I've kind of got everything in the diffraction pattern and maybe in the PDF, but we know that we found metallic nickel in the previous case. And so I can already go in and search for that. And I do find a small, albeit more difficult to see by eye peak around 2.5 angstroms. And actually in this case, we do also find metallic cobalt. And I can say, I don't show it here, but we also find this, for instance, in XPS results. So we know it's there and we expect it. And that's something that you really just can't see in the diffraction pattern. There's no chance to realistically find that. And so that's already a nice bit of sensitivity that we have in the separation of the peaks at low distances. And again, now we go in and feel reasonably confident that we've gotten everything that we can find there. There's probably improvements you can make, but I feel quite good about that. But now you look at the quantitative estimations that you get, and you actually see quite large discrepancies in the amounts, particularly of the Quartzite and sphalerite type cobalt oxide. Okay, I mean, we don't have the cobalt, but that's only a couple of percent. But what is the issue here? And the issue is that there's actually a very significant population of very small domains of the Quartzite type. Okay, and you just don't see that in the diffraction pattern. And what is the reason for that? Well, the reason is, as I mentioned earlier, there's lots of other contributions to the diffuse scattering in the full diffraction pattern that we measure, lots that don't contain structural information. And then you also have lots of overlapping diffuse signals from these different nanophases. So you have lots of overlapping, broadly varying signals, and it's very difficult to accurately partition out these components. Okay, so if I have a very slowly varying signal from 1 nanometer particles present, I don't know that that's not getting subsumed into my sort of baseline estimation. And so what is the advantage of PDF? With PDF, through the processing of the data, we're removing those other scattering components that don't contain structural information. And so this gives us a better sensitivity to those components that we otherwise miss sort of in fitting baselines with the diffraction pattern. Okay, and now I just want to show one more example, which is the case where they add a bit of platinum into this system. So actually just about 4 weight percent. And I don't go too much into the catalyst performance side of this, but I think it's quite interesting then that they see actually a performance that in some respects is even better than a comparison point of a 20 weight percent platinum system on carbon. So really even just adding a little bit of platinum to this system in combination with the nickel cobalt oxide actually already has some kind of effects in the way that they mix together, in the way that they form particles, that's quite advantageous for the performance of the catalyst. And you can see, okay, there's quite large, kind of cobalt particles, and there might be some core shell formations with the cobalt nickel, and then we have quite small domains of platinum. And so we want to see that in the diffraction as well. So diffraction looks complicated, actually. We see, okay, there's metallic nickel cobalt, actually more substantial than in the previous cases, and definitely larger domain size. But now we have to actually really use some additional information to kind of figure out the rest of this, right? So fortunately, we have lots of pre-knowledge here, so we can guess again that there's this sodium chloride type nickel cobalt oxide. So that would be quite relatively difficult to assess without any other information, but we kind of expect it to be there. But where's the platinum going? And actually what's happening is it's hard to see here, but there's additional intensity here. There's an additional peak sort of between this first green peak and the second black peak in the PDF. And we can identify that from the difference curve. And that's actually coming from like a solid solution with nickel, cobalt, and platinum. And you can see in the diffraction pattern that this is extremely broad. This is very, very small, about 1 nanometer, maybe less domain size coherence. And there's just no chance of indexing that from search match from the diffraction pattern alone. So the whole benefit is being able to iterate between real space and reciprocal space to check the matching of these components and look for things that you're missing, okay? And now we can look at the same thing here. And again, this is even more complicated in terms of discrepancies in weight fractions, because it's sort of like you would be missing this whole platinum component if you didn't have the PDF available, and you run into similar issues with both the the partitioning of diffuse intensities with effects of surface structure and morphology, and also the idea that, particularly in the platinum nickel cobalt case, it's difficult to really know how much platinum is there. So you can do things like check Vagard's law for, where the lattice parameter falls in between, sort of pure nickel cobalt versus platinum. But you also have to deal with the fact that these are ultra small domains, and you don't 100% know whether they're discrete particles or whether they're showing up on surfaces of larger particles, and these things can all affect the distance as well. So that is a point of error that you have to be aware of. So some key takeaways of this: well, accuracy of Rietveld refinement generally starts to break down for very small nanoparticles, because you're assuming essentially modifications to lines predicted from a system or a model with infinite periodicity. And that's not how the scattering works. You have continuous scattering profiles that have substantial effects from defects in surfaces and the shape of the particles. The other issue, again, is that it's very difficult to partition the different contributions to diffuse scattering when you have many components of that nature that are all overlapping. And so the benefits of the PDF are that you maintain a high sensitivity to the different coordination environments, regardless of the domain size, and also regardless essentially of kind of like long-range defect structures or surfaces that are forming or particle shape. And for that reason, you're also much more robust against the effects of the microstructure, although you do have information present there that you can use. Okay, so now I'm going to kind of switch from nanoparticles back to bulk structures, because PDF can also be used for bulk crystal structures as well. This is another project that was with Thomas Lunkenbein, who was at the Fritz Haber Institute, now at Uni Bayreuth. And they do some really awesome electron microscopy work. And they were looking at these kind of ternary molybdenum vanadate and quinary sort of multi-metal oxide systems that are used for the production of olefins and other hydrocarbons. And basically what they find sort of performance-wise is that this quinary oxide is more selective for propylene and acrylic acid. And what is the reason for that? Well, they think, and I'll show, molybdenum vanadate is more rigid, and it actually leads to more defective surfaces. It's more active, but it's less selective for the same reactions. So it depends on how you run the catalysis. So one material might be better for different applications. But the idea is that basically the bulk structure acts as a support for the surface restructuring, and that comes into play during the operation of these materials. So the idea is that the bulk structure actually sort of lends into how the surface restructures while you're operating the materials. And we want to get some clues into that based on actually the local structure of the bulk as well, okay? So you can do standard things like X-ray powder diffraction, do Rietveld refinement, and we can fit this layered molybdenum vanadate structure with or without doping. And the interesting thing is that when you look at the electron microscopy, you get behavior like this, where the molybdenum vanadate structure has these really kind of irregular, amorphous looking surfaces, whereas the quinary oxide has quite regular, nice, flat surfaces. And so it almost seems counterintuitive when you have more complexity in the system. So what do we do? With PDF, we can now determine a starting model from powder diffraction. And what we actually want to do is see how well that sort of average structure model agrees with the local structure over different correlation length scales. And so we do this kind of sliding minimum, or sometimes we do what's called boxcar fitting. But we're basically fitting that model over different length scales to see how well it matches the structuring on those length scales. And as we include more information in the very local structure, we find that the model agrees less and less with the local structure. So it says that locally, the structure is actually deviating quite a bit because of localized defects or structural distortions versus the average structure. Okay, and this is actually even worse for the keen area oxide. So the average structure agrees even less with the local structure in that case. And there's another thing that we can do now, which is testing how much do we need to sort of relax the average structure to get a good model for the local structure. And so in this case, what we do is actually allow the atomic site positions to refine, and we can do that for different substructure components to see what is most important in terms of localized distortions. And then we can see how that tracks as a function of how much we allow these things to distort off of their average structure positions. So as we do that, we find that actually refining the metal substructure is the most important towards getting a better agreement. And so it suggests that there's mostly frustration in this kind of metal-metal substructure. And also, again, we need larger displacements for the keen area oxide to actually get a good fit. So what it all means is that the keen area oxide is deviating more from the average structure than the ternary. And that's totally expected, right? Because I have more metals present that can occupy the same sites. And of course, when I think about, average structures, we sort of just put like, partial occupancy of different atoms on the same site, but then otherwise treat it the same. But in reality, if you're looking locally at this system, if I have a molybdenum atom if we go back here in this kind of pentagonal coordination position, this yellow S9 position, versus if I have niobium sitting there, then the metal oxygen distances and the angles and everything is going to relax differently. So it's the structure of those sites is actually different. And I don't really capture that well in the average structure. And so if I have more possibilities for localized sites, then I have more extensive and different distributions of relaxation happening. And so what that means is that I have a less rigid structure, more relaxation happening in the bulk of the keen area oxide. And this is actually allowing the surface to restructure. And this is why you can actually get sort of a more regular surface for the keen area oxide. And actually it exposes these niobium sites in a different way. And that allows you to sort of change the reaction chemistry a bit. So that's why you can get different behavior. Okay, so again, for this key takeaways, structural disorder is also present in bulk crystals, not just nanocrystals. And again, you run into similar issues with sort of standard Rietveld refinements. You don't capture these things very well because of this averaging effect. So if you want to look at like, how does occupational disorder actually lead to distributions of local structure environments, it's difficult to capture with Rietveld refinement. And so PDF allows you both to look at the very local structure and see how these coordination environments are structured. And it also gives you this benefit of testing the structure over different correlation length scales. So you can see how well can you predict different site positions over different length scales, and thereby understand like where in your structure are these effects taking place, and then correlating that with things like electron microscopy or elemental mapping allows you to get a much more comprehensive understanding of how the system is behaving. Okay, and now the final example I'll try to go through a little bit more quickly because I want to leave some time for questions, is differential analysis. And this has to do more with the topic of kind of site isolated catalysts. So we're thinking about catalytic complexes like metal organic complexes and also single atom catalysts. And so I just give some examples here where, people are looking at these kind of complexes for CO2 reduction. And for instance, the elements shown in red are kind of proven for photochemical CO2 reduction. And the idea is that you basically want to implant these complexes into some kind of support material because you want to prevent the reaggregation of the metals and the reformation of nanoparticles during operation so that you can have a better cycle life of these materials. So again, we're talking about, putting these things into supports and extracting relatively dilute signals. And so how do we do that? Well, we use this different pair distribution function method. And the idea here is that we have a small amount of our target catalyst material present in the support. And we want to actually just specifically understand the coordination environment of those active sites. So we need to remove all of the kind of extraneous information from the support itself, because we don't really care so much about the support and it's masking the part that we're interested in. And so conceptually, an easy way to do this is if you measure a reference pattern for the support without any of the catalyst sites loaded, and then you measure a target material which has the catalytic sites loaded into the support. And so you get these different partial contributions where the reference is just the host-host correlations. And now the target material has host-host correlations as well, but it also has guest-host correlations, and it also has guest-guest correlations. And then we actually subtract these. And if I don't make any assumptions yet, now I have guest-guest, guest-host, and actually the differential between the host-host correlations between those two samples. So I can make a few assumptions to say, okay, well, if the guest contribution is sufficiently dilute, then I can sort of neglect the guest-guest correlations, at least on the very local length scales. And if I can assume that the host structure doesn't change, which again, if I have a very dilute amount of the catalytic sites, and also if the support material is subjected to the same synthesis and processing conditions, this oftentimes is a sufficient assumption. And then for the local environment of the catalytic site, I can predict different possibilities for the binding coordination and make models for those, and I can actually test those models against the data. And so, one way that you do this experiment is with this so-called differential anomalous approach. And this is where you actually take advantage of anomalous scattering and you change the energy of your X-rays during the experiment close to, but just above the absorption edge, so that your kind of scattering power from your target atom is changing drastically, and the rest of your support scattering is not changing at all, so you can subtract those. The disadvantage of this, of course, is that for not all elements do you have a convenient edge that you can do this on. And so, if we go back to looking here, the K edge, for instance, for manganese to copper here is sort of like in the range of 7 or 8 keV. Molybdenum to palladium, I think, is on the order of like 20 to 22 keV. And tungsten to iridium is probably, I think it's around like 74, 75 keV. So for kind of the 4D and 5D, you're in energy ranges where you can potentially do PDF measurements, but for the 3D metals, you don't really have a convenient way to do that and be able to do PDF measurements on it. Okay, so that's the idea. The other is, of course, like if you want to do this energy change approach, the experiments are more complicated. So an example of this is actually with my former colleagues from the Max Planck Institute, and they're really interested in incorporating different types of catalytic complexes into covalent organic frameworks. And in this case, Andres here was working on loading these palladium complexes into a covalent organic framework for hydrogen peroxide production, in particular, getting it into a range where you can use a good portion of the solar spectrum to work well for the photocatalytic reaction. And they want to basically identify that they successfully incorporate these complexes into the framework, and also understand a bit about how that affects the host material structure. So again, you can do microscopy and elemental mapping and see, okay, well, I still have this sort of crystalline covalent organic framework support, and I can see I have a pretty homogeneous distribution of platinum and chlorine, so I can see that my complex is distributed throughout there, but it's difficult to get more information about exactly what's going on locally. And why do we care? Because actually also the covalent organic framework support, even though it's technically crystalline, also has a lot of stacking fault defects, and we don't know exactly how these things bind to the branches and how that affects sort of the stacking relationship of the layers. So locally, we have the binding, but then you also imagine there might be correlations coming from neighboring layers or modifications to the layers as well. So poor host crystallinity, aperiodicity of the binding sites is important, because if the binding sites were periodic, again, you could just do sort of like straightforward crystallography on this, but you don't have the conditions for that. And again, you get kind of weak scattering from low loading. So again, we first look at the diffraction, and you see a few interesting things here. One is that between the loaded and unloaded framework, if I look at the 100 reflection, I actually see that I have a contraction. So my Bragg reflection is actually moving to higher angles when I load the palladium complex. And you actually see the same thing in the 001 reflection. You see a contraction. And that's kind of interesting, because the general expectation would probably be that, well, if I load something into the framework, it should probably expand. So that's interesting. And then for some of the other reflections, we see modulations in intensities, and that comes from the phase contrast between the presence of these palladium complexes. So we look at the PDF now, and I don't get into the details of how we do these normalizations, but basically there are features where you have an expectation for consistent intensity, and we can normalize the patterns by these peaks so that you can get a proper subtraction of the host support. And so once we do that, then we have a reference pattern that we can compare against simulations from our different models. So the first thing that we look at is, well, we don't want palladium nanoparticles in our system. So we can look for the peak that would correspond to metallic palladium. Unfortunately, we don't see that. And then we have different models for sort of planar COF branches with our complex bound, and then also ones where the presence of the complex actually induces conformational distortions. And we find a better agreement with that. And that is great, because it explains why we have this contraction, because if your conformation, your kind of torsion angles in plane become more twisted, this actually allows to explain why you can get sort of a smaller repeat distance in the stacking, and also in plane of the layers. Okay. And we also did quite a bit more systematic studies of this in terms of data quality, in terms of what works best for these kind of differential methods. And you can see here different preparations and measurements. So from a lab measurement done for 2.5 days to synchrotron measurements for 30-minute scans with different amounts of sample and levels of compaction. And actually you can see that the effects are quite sensitive. So you really need high statistics data. You really need good preparation of the samples to be able to extract out these residual signals. And you can see when you do satisfy those conditions, you do have a really high sensitivity. So in the plot on the far right, you have 3 samples where you go from 1.3 to 0.9 to 0.5 weight percent loading of palladium into this other polymer system, and you're able to reliably extract out those peaks, and also show that we don't have palladium bonds. Okay, so key takeaways here: this is really not something you can reliably do from the powder diffraction patterns or with any kind of standard fitting techniques, because it's just extremely broad signals, and there's no assumptions within sort of like the Bragg kind of setup of how we do those refinements that really helps you kind of extract this information. So again, PDF, very sensitive to local structure. We can extract out the support signals and reliably look at the coordination of these particular partial contributions. Okay, so just quickly, key takeaways: total scattering. It's a modified powder diffraction measurement, but you need really good statistics and really, really high Qmax to get the best results out of this. But it also should be done with good diffraction measurements, with standard analysis to get the most information on your systems. And the PDF is a convenient way to analyze the total scattering data. And you have a high sensitivity to phase identification in nanosystems. You can look at structural distortions in bulk crystals, and you can also extract out binding configurations from single atom catalysts and complexes. So with that, I will turn it back over to Sebastian, and he will tell you a little bit about how we can get measurements for you guys.
Yeah. So thank you, Max. I think you all saw why we wanted to come to start early. Yeah. So we have 5 minutes left. I will keep it short here. So one of the kind of like the most important things is, right, yeah, like why wouldn't you use PDF? Most people don't do it because they don't have access to the machine. If you don't know how to do the analysis just yet, it's very hard to make sense of the data, as we saw, and many people are maybe not sure. So what we provide here as momentum transfer is we actually have biweekly access to one of the best synchrotrons on the planet, the ESRF, and we perform the analysis. We can perform the analysis for you, so you don't have to worry about this, or we connect you to one of our collaborators. We also offer weekly sessions with Max to actually walk you through a couple of your questions, and in order to absolutely reduce any doubt in your mind if this could be something or if this should be something you want to try, we offer the first 5 samples for free. So you can just send them over and we measure. You can look at them, and if you need, we can help you with the analysis. So in order to do that, you can book a short call with Max and myself. Use this QR code. I also post in the link in the chat. If you do it now, kind of like we can meet up in the next 2 weeks and discuss your samples if it makes sense, how it makes sense. And our next beam time is on Monday, so you probably don't make that. Tuesday, you probably don't make that, but next one after that is early February, and so you could have data by mid-February if you send samples too. So the link is there, and if since we are running out of time, if you have additional questions, you can also book a meeting with us and discuss it, or you come to our Wednesday session. So how do we work? Just to be quick, so as I said, we schedule bi-weekly at the ESRF. It's really simple. You send us your sample, we prepare them. As we said, preparation is pretty important. Prepared, we measure, and we provide the data the best possible way. So you have all the background subtracted, you have the NIST standard measurements with it, and that will provide you access to the PDF and to XRD, high resolution XRD measurements. So yeah, book a call, send samples, get a result, and this is our team. We have extensive expertise here. We can help you with all kinds of questions. So with this, I would thank you all for your attention, and we have already 2 questions. One is from Shatanu. What is the maximum spatial resolution possible for X-ray PDF, and what are the methods to improve the spatial resolution?
Yeah, good question. So this really depends on to what maximum Q value you can collect data to, such that the statistics on the coherent signal are good enough to kind of keep in your data. So for our setup, we collect to about 30 inverse angstroms. And that course, I mean, it's basically like pi over Q max is roughly your spatial resolution. So I think it's about like 0.12 angstrom, like bin spacing in the PDF that's actually meaningful. So that means you can see sub angstrom differences in bond positions. There are setups where potentially you can go higher than that, but for X-rays, it is generally quite difficult to go much higher than that because of the Q dependence of the X-ray form factors. So you can do neutrons, and then you have constant neutron scattering lengths, and typically you can collect to much higher Q values, but it's also much more difficult to get access to neutrons, and measurements are longer and more complicated.
So I think we have time for one last question, and that is there a possibility to perform in situ PDF under the operating conditions?
Yeah, absolutely. We don't currently offer that. We're working in a sort of high throughput format for ex situ ambient conditions, but definitely, I mean, any conditions that you can do a powder diffraction measurement under, within reason, you can do a PDF measurement on. I would say the ones where it maybe gets a bit tricky and I haven't seen much progress on yet, although maybe there is and I haven't seen it, is like, high pressure diamond anvil cell. That gets to be a bit tricky. And then also working with sort of like milling devices where you maybe have limitations on the outgoing angle, and then also lots of kind of extra signals coming from your milling materials and the apparatus itself. So those get a bit difficult. But yeah, high temperature, low temperature, lots of beamlines have giant, 6-7 Tesla magnets that you can apply to your materials. There's all kinds of things that you can do there.
Okay. So I think we are out of time.
Sebastian, I mean, we still have 30 people. I want to just give one last offer to see if anybody else has any other questions that they want to ask.
No, absolutely. If you're like right now, there's nothing. Maybe can you talk about time resolution in terms of what is the exposure time we have usually? So people have a.
Well, I mean, in our case, the exposure time is not so relevant. I mean, we just measure to get good statistics on the data. We're not doing sort of in situ measurements. So there's nothing from our measurements that's going to give you time resolution in that sense. But for a similar setup, if you wanted to do like a time dependent measurement, it depends on the type of materials that you're looking at and how well they scatter. But there are some setups that can go, sub-second resolution in terms of what you can track. And if people are interested in that, you can certainly contact me. We've done a lot of work in sort of like nucleation of metal organic frameworks and transformations happening at temperature. And in those cases, you can really see structural progressions of these sort of like nano phases and stuff like that. It's a really powerful technique.
Oh, brilliant. All right. So there's one more question again from Shantanu. Regarding resolution in STEM PDF, the resolution is limited by probe size, which is often 1 nanometer to prevent disk overlap.
I'm not sure what you mean by, do you mean like calculating the PDF from a STM image? I'm not sure.
We can see if kind of like maybe Shantanu wants to NBED. Maybe I can find him and get him on stage.
Oh, you mean like electron diffraction PDF? Yeah, I mean, I think you will not get as good resolution with the electron PDF because actually just doing the processing for it is much trickier. I think there's still a lot of work going into making PDF from electron diffraction more quantitatively accurate. But I know that there's the benefit of that technique, obviously, is that you can do spatial mapping at a very fine distance.
I cannot unmute you. You have to unmute yourself. But I can send you a request.
Hi. Yeah, okay. So can you hear?
Yes.
Yes.
Yeah, so what I was looking for, I'm basically a macroscopy person.
Mhm.
So there was a STEM PDF like developed by Professor Christian Kuber from KIT. So
Mhm.
what they do is they they record the nanobeam diffraction patterns as a function of probe position. So and if you have very highly converged probe, for example like sub-angstrom or one angstrom, so
Mhm.
you have the seabed disk overlap on the backfocal plane, so which complicates your PDF analysis. So they restrict the probe size to the nanoscale, like so nanobeam electron diffraction, and they they record the diffraction pattern at each probe position, and then then they perform this PDF calculation. They can also do PDF mapping. So because of the probe size is very large, the 1 nanometer, so it averages the information over the illumination area. So that prevents high spatial resolution. So in terms of that, if you can perform like STXM, for example, like you have focused X-ray beam. So so you will get the similar pattern, like the X-ray diffraction pattern, the convergent beam X-ray diffraction pattern. So, but is there any way to deconvolve this overlap in order to get maximum of the PDF at high spatial resolution? That's what I wanted to.
One thing that I think it's important to specify is that these are two different resolutions that we're talking about, right? Because one is actually like spatial resolution if you're mapping out the structure of your sample in different locations, and the other is actual spatial resolution in the data, like how up to what resolution can you resolve atomic distances. So there's two different things going on there in terms of like best methods for improving the spatial resolution in electron PDF measurements. I don't really know. I'm not a microscopist, so I don't really know like what are the kind of state of the art methods in that respect to improve that. But yeah, I mean, I think I know Xiaoke Mu and, as you said, Kobo, and there's a few other people that are doing quite extensive work on electron PDF mapping. Simon has also done quite a bit of work there. So I think you can look to those papers to see kind of what people are saying.
Yeah, so there are two resolution in terms of the information you get in the PDF map or the PDF data, and one which is limited by the probe size or the volume of the sample that you are sampling.
Mhm.
So these are two factors.
So we have one more question. Thank you,
Yeah.
Shantanu. I will kind of throw you off the stage. Don't take it personal. So then we have one more question, and that is, which software do you use for Face ID that allows for user-defined wavelength? That is fun. Sikum Uzo.
Yeah, so I mean, for Phase ID, right now I'm typically using the Sieve tool in the PDF5 Plus database. And maybe you've also seen we've put some posts on it, but we're actually developing a search match tool to work in our platform, and we'll be releasing a version of that probably by the end of the month, and that will be sort of seamlessly working with data that you collect with us coming back into your account in the web application. So to start, that will host structures from the COD. So we'll be a little bit more limited in terms of what you have in the database, but we'll also be connecting the PDF database to that as well. Although, of course, then you'll have to have a license to the PDF database. But I hope that will help sort of streamline search match applications for data that you collect with us. And we'll probably let you use it on data not collected with us in the near future as well. But we have to make some modifications to make sure it's working well for you guys.
So I think that answers a part of Adrian's question, because he also asked about the XRD face identification tool.
Yeah. So basically, by end of January, we should have sort of a beta version released for you guys to play with.
So yeah, register on the site to get access, and if you have not measured your data with us, send us samples now, and you can use our tool right away for that.
Yeah,
as well.
and we'll make another announcement too once it's released, just to let you know that it's there.
No, absolutely. Yeah. So, any more questions? This was really nice. Thanks a lot. Thanks a lot for everybody coming up. All the questions. Thank you, Max. Great talk. Very dense. And we will send out the invites for everybody who is interested in meeting us, and hope we see you in 2 weeks for our more analysis focused talk on PDF and our future webinars. Thanks a lot, and have a great day.